Okay, according to the clock on this computer, it's 2:15, so we'll get underway. Good afternoon, everyone. Welcome to the Tuesday afternoon briefing at the 228th meeting of the American Astronomical Society here in sunny San Diego, California, though it's not actually all that sunny today. I'm Rick Fienberg. I'm the AAS press officer, and I'm glad to see you all here. And we also have an audience watching on the web via webcast. For those of you who are online, if you have any questions, you can use the text chat box to let us know what those are. And if you have any technical problems with the webcast, please let us know via the text chat. Please, if you have cell phones or pagers or anything, please silence them now. Well, this is a briefing that's on three different topics, but they're all related in the sense that they cause us to think hard about astronomy and what the universe is like and what it would be like if we couldn't see it, and what it might be like if there were other people like us out there somewhere. So it's dark skies, aliens, and the multiverse. We have three very interesting presentations. We'll first hear from Dr. Craine from STEM Laboratory in Tucson. He'll talk about an approach to objectively defining and ranking dark night communities. Then we'll hear from Evan Solomonides from Cornell University, who's going to share with us a probabilistic analysis of the Fermi Paradox, the one that asks, where is everybody? And then Sean Carroll from Caltech, who many of you I know will be familiar with from his books and his many blog entries and other very effective outreach to astronomers and the public, will speak about whether normal science is possible in a multiverse. He'll be touching on a debate about the very nature of science. And I asked Sean to come because there's a special session here at the meeting about cosmology and the future of cosmology. So he's representing that session. So I'm going to turn it over to Eric first, and then we'll hear from each of the three speakers, and then we'll do questions at the end. And just so you know, we're going to have questions for Sean Carroll at the beginning of the Q&A period, because he then has to rush out. So we'll give him first crack at questions. All right, Eric Craine.
Thank you, Rick. A group of colleagues and I have been making various quantitative measurements of artificial light at night for quite a number of years now. And we have recently produced a light at night index, which we call LANI, which is a satellite-derived evaluation of the efficiency with which communities implement artificial light at night. The LANI index is computed for every community in the United States with a population over 500, which is about 19,300 or so communities. The index takes into consideration the total radiance of the community that's being measured, and that's simply a measure of the light that's radiated upwards from the community and observed by the satellite. It also takes into consideration the population of the community, the number of housing units, the physical area of the community, and it takes all of these economic factors together to create a weighted LANI score. And that score we then report as a percentile ranking for the communities that we're interested in. The LANI metric is calculated to vary between 0 and 100, with larger numbers representing communities that are much more efficiently lit. As astronomers, we are very interested in dark skies, of course, but it's important to recognize that although the LANI index is a coarse surrogate for dark skies, it's really a much more useful metric than that. It should be more correctly thought of as a measure of the lighting efficiency, as shown here in this map for the state of Arizona. So why is this important? Lighting technology is changing very rapidly, particularly with the advent of cost-effective and generally efficient light-emitting diode LED fixtures. Community planners across the United States are involved in lighting retrofits right now, an exercise that may offer only one opportunity to get it right for many years to come. The Lanai metric is a powerful tool to target communities that would benefit from thoughtful new lighting installations and to establish priorities in light at night mitigation. Further, the Lanai metric is ultimately a temporal evaluation. That is, it allows us to follow trends in night lighting over a period of time. Such a database is useful, for example, in making long-term funding decisions for astronomical observatories, but it is really invaluable for correlation with other databases that may be affected by light at night trends. Databases such as human populations, disease epidemiology, and ecology related to nocturnal animal behaviors in response to artificial light. The Lanai dark community rankings provide a useful guide to areas where more comprehensive measurements of light at night can be valuable. In such cases, we use a range of measurement protocols, including ground-based photometric surveys, airborne observations, satellite data, and spectroscopic surveys to evaluate impacts of color on night lighting. We've done this type of light at night mapping around observatory facilities in Arizona, California, and Hawaii. Most recently in Hawaii, we've been able to quantify significant improvements resulting from specific LED streetlight retrofits in Waikoloa, which is near the Mauna Kea observatories. So how can these Lanai scores be used? Well, there are a variety of different ways to analyze and implement Lanai data. And I'm going to show here quickly just one example of a variety of professional and private observatories in the United States. The metric that's plotted here is the percentile ranking of Lanai scores compared with the other 19,000 communities in the United States. The blue point is the average Lanai value for all communities within 80 kilometers of the observatory of interest. That is a radius of about 50 miles. The orange point is the percentile Lanai value of the community in that group, which is nearest to the observatory. And the bars here represent standard deviation around the average observatory community value, and so give an idea of the general range of brightnesses of nearby communities. Observatories with lower percentile Lanai values are impacted by very low efficiency lighting and represent some once great observatories that are now basically disabled by light pollution. They include Perkins Observatory, Mount Wilson Observatory, and a number of other observatories that you'll recognize. At the other extreme, which I cannot get to come up here, at the other extreme, we find prominent observatories, mostly in Hawaii and Arizona. So note that the nearest community ranking can give an idea of the potential values of mitigation in community lighting, some with good opportunities and others with serious potential problems. For example, Kitt Peak National Observatory, which is located, let's see, is that? So Kitt Peak National Observatory located here, really has a very mediocre ranking, but the neighboring communities are even more poorly illuminated. And so this suggests that with an effort in those communities, the observatory prospects could be improved somewhat. At the other extreme, in contrast, is Mauna Kea Observatory, which has a very good rating, but also with excellent ratings for neighboring communities. So the challenge here is to figure out how to maintain those good Lanai ratings in concert with diligent monitoring of lighting trends. So in summary, the Lanai metric is not a dark sky measurement. It is a much more useful efficiency measurement that allows us to measure and monitor wasted energy in communities and also identify areas for cost savings, which in the final analysis for most community planners is the real driving factor for putting good lighting in their communities. It is a unique community planning tool, and it is a useful research tool for multiple systems that are affected by light at night. I'd like to bring to your attention the URL at the bottom of this slide, which provides a connection to a more detailed description of the Lanai metric. It also lets you look at interactive maps of Lanai distributions, both around American observatories and examples of these data files for just various communities of interest. I'd like to thank you for your interest here, and I'll be happy to be available for questions at any point. Thank you.
Hello, my name is Evan Solomonides. I am an undergraduate student at Cornell University, and I worked on the paper A Probabilistic Analysis of the Fermi Paradox with Professor Yervant Terzian, who is also at Cornell University. This project was funded by the NASA Space Grants Consortium, the New York Consortium, and my email is available if you have any questions or would like to arrange any sort of coverage for this. So first, what is the Fermi Paradox? So we are on an incredibly ordinary planet around an incredibly ordinary star, about 2/3 of the way along an ordinary arm of an ordinary spiral galaxy. There is nothing even remotely special about where we are in the universe, or even the galaxy. So there shouldn't be anything that special about us. That's called the Mediocrity Principle. Because of this, life should be fairly common. We shouldn't be the only life in the universe. It should be elsewhere. So the Fermi Paradox asks, where is everybody? And what we did to take a look at this is we took a look at how far our broadcasts have actually reached into the galaxy. And if you can see here, this tiny little blue dot, Okay, the tiny little blue dot in the box on the bottom right is a zoomed in version of the tinier still blue dot in the actual artist rendition of the Milky Way. And this tiny little dot is actually significantly bigger than the total area of the galaxy that we have reached. The first broadcast in 1936, the first broadcast powerful enough to leave our atmosphere. We have reached an insignificantly small portion of the galaxy. And with this in mind, the Fermi Paradox starts to make a little bit more sense. We haven't heard from anyone because space is very, very big and it takes a very long time for communication to reach anything of note, even traveling at the speed of light. So we then conducted a statistical probabilistic analysis, and we looked at, given an average length of communicating history, broadcasting history, and a number of civilizations in the galaxy, how much of the galaxy would have been reached. and we set the portion of the galaxy that would have been reached for a given number of civilizations and a given average length of history. We set that portion of the Milky Way under 1/2, because if more than half of the Milky Way had been contacted, we would expect to. By the Mediocrity Principle, since we're in such an ordinary spot in the galaxy, we should hear when about half of the galaxy hears, or when about a majority hears. We used this inequality that we derived to make some predictions. We assumed that we were exactly average, which is the extreme of mediocrity. We used ourselves as the complete average. And if we were the complete average, about 1/10 of 1% of the Milky Way would have been reached, given the predictions that we made using the inequality. With that small a portion, if we had been contacted by another civilization, we actually would be special. And that would begin to actually violate the Mediocrity Principle, which is something that we typically try to avoid. By this model, which again is just a model, the Fermi Paradox is not actually much of a paradox, it's not much of a mystery, until 1,500 years have elapsed. That is when we predict that half of the galaxy would have been reached, and at that point, if a majority of people had heard and we hadn't, why are we special? Why aren't we hearing yet? Until then, it is expected, understood, and reasonable that we have not heard. Our conclusions then are that the Fermi Paradox was not, in fact, much of a paradox. The results of our apparent loneliness are expected for another 1,500 years by this model. By the Mediocrity Principle, then, we can claim that we are most likely not alone in the galaxy, and the immense size of even our ordinary galaxy makes it such that communicating with anybody is just an incredibly slow, long duration endeavor, and we should keep broadcasting, we should keep listening, because if we don't, we may miss our chance to reach somebody or be reached by somebody, but we shouldn't expect a result for quite some time. The full paper with the derivation, the references, the calculations is available on arXiv at the link on this slide. And once again, my name is Evan Solomonides. I worked with Yervant Terzian at Cornell University. This was funded by the NASA Space Grants Program, and that is my email. I look forward to any questions that you have. Thank you very much.
Should I stand up? Or all right. I don't have any slides, so
Blank this out.
blank it out. Thank you. So I'm Sean Carroll at Caltech, seancarroll@gmail.com, and I'm kind of standing in for both myself and for Joe Silk, who was hoping to be here today but is chairing an afternoon session that is going on right now. And the reason we're here is a little bit different than most of the press conferences that you might expect to attend. We have no new results to announce, no pictures to talk about. It is a set of ideas in theoretical cosmology or even philosophy that are being talked about. And although progress in theoretical work such as this is more gradual than that in experimental or observational work, it does kind of happen. The dialogue does kind of change. And so Joe got together with Virginia Trimble and Roger Blanford and organized a meeting within a meeting at this AAS meeting on the question of limits of scientific cosmology. In particular, the worry, if Joe were here, we conjured him up, he would express a concern that certain cosmologists, like me, have gone too far in how we think about the universe and what we count as scientific exploration of it. The point being that we understand an enormous amount about the part of the universe we can observe. When I came into graduate school in the late 1980s, we were not very good at describing the universe. It is some kind of anthropic coincidence that our progress in understanding has coincided with my professional career as a scientist. I don't get all the credit for doing this, but honestly, in 1988, we did not know the Hubble constant to within a factor of 2. We did not know the geometry of the universe or the density of the universe to even worse than that, and there were many people who thought that we would never know. We had not yet discovered the dark energy. We had not yet discovered the anisotropies in the cosmic microwave background. In the last almost 30 years, we've done all of those things. We now know the inventory of the universe. We know the cosmological parameters. We're debating about percent level measurements. And we're learning a tremendous amount about the details of structure formation, dark matter dynamics, and so forth. So if Joe were here, he would say, that's great. He contributed a great amount to that very work. But some people, being either impatient or overly ambitious, want to talk about parts of the universe that we literally can't see. The extent of the universe beyond our observable horizon. The universe is only 13.8 billion years old, and we use light to see the universe, and light travels at a finite speed, 1 light year per year. Therefore, objects that are far enough away are in principle unobservable. And certain cosmologists want to talk about the possibility that even though our universe within its observable patch is very smooth and uniform, outside what we can see, the universe might be very, very different from place to place. Not only cosmological parameters, but even physical parameters like the masses of particles or the energy density of the vacuum. And so the people who are a little bit worried bring up the criterion of falsifiability. They say the idea that there is a multiverse, that there are regions outside what we can see where conditions are very different, are in principle unfalsifiable. You will never be able to do an experiment that tells you that's not true. Therefore, it's not part of science. And the point that I tried to make in this session this morning, and what we're going to be debating both right now as we're speaking and then tomorrow morning and tomorrow afternoon is, but nevertheless, the universe could be that way. Therefore, we have to take that possibility seriously and ask how it does affect the parts of the universe that we can observe. And that is exactly what we are doing right now, and that in fact, it's not in any sense a change in the parameters of science or a new way of calling what is science or is what not science. It's just that the old-fashioned idea that Karl Popper's criterion of falsifiability was really what demarcated science from non-science was never really completely accurate. And in the modern world, we have to be a little bit more sophisticated about how science works. When people study the multiverse, they're just doing ordinary science. It's hard to do it because we have to be indirect. We cannot do a decisive experiment quite as easily, but it's still presenting theories, developing them, and ultimately asking which theories provide the best explanations for the data. So one point about this that I like to emphasize is to contrast not the observational progress we've made over the last 30 years, but the theoretical progress. So in 1988, when I entered graduate school, I was in an astronomy department. Nobody there believed in what we call inflationary cosmology, the idea that the very early universe was propelled by a temporary period of super dark energy to expand by an enormous amount and basically flatten out. This was an idea put forward by Alan Guth circa 1980, and it was beloved by theoretical physicists because it was very elegant, very simple, it solved some problems. But the working astronomers said, yes, but it makes no predictions. It's just a cute idea. And the one prediction that it arguably makes about the density of matter in the universe is clearly wrong. We've measured the density of the universe and it's not the right answer. Since then, in fact, that one prediction about the density of the universe turns out to be right after all, because we found the dark energy, which was a missing component to the energy density of the universe. And we've measured the perturbations in the cosmic microwave background and in large-scale structure, which are additional predictions of inflation, and they all fit exactly what you might expect. So today, to astronomers, inflation is accepted. If you see ever one of those artistic drawings of the history of the universe, it always begins with inflation, even though we don't know for sure that inflation actually happened. Meanwhile, the part that you're not told is that many theoretical physicists have become more dubious than they were in 1988 about whether or not inflation actually works. When you think harder about what inflation says, you realize that it does not predict that the universe is flat, that there are a scale-free density perturbation spectrum or anything like that. What inflation really predicts is the existence of a multiverse. Inflation, once it starts in almost all models, tends to continue on, and in different parts of the universe will give you different physical conditions. To understand what you expect to be the most likely outcome of inflation requires that you think about not just the universe, but the multiverse. The possibility that there are different regions with different conditions, and we have to ask probabilistic statements about what are you likely to observe given that you see certain things already around you. Right now, we're not very good at that. Something that is an absolutely fair critique of the multiverse is that it is not a very well-developed, rigorous theory. We don't have the tools, we don't have the math, we don't have the understanding of quantum gravity, string theory, or inflation to turn these promising ideas into absolutely quantitative predictions quite yet. But at the same time, it's not fair to claim success for inflation for predicting certain things when really it doesn't. So cosmology is in a very, very interesting state right now that we are trying to climb our way out of, where we have a really, really good way of talking about the universe we see that seems naively to fit in a very attractive paradigm for an inflationary beginning, but upon closer examination, that paradigm doesn't quite say what we want it to say. It's going to require both much better theorizing and much more experimental data before we can figure out these puzzles once and for all. Thanks.
Well, it's good to know there's still some job security for theoretical cosmology.
Full employment.
Okay, so as I mentioned at the beginning, I'd like to direct any questions that we have for Sean Carroll first, because he's got to scoot to another room. So if there are any questions here in the room for Sean, please bring those up first, and then we'll move on to questions for the other speakers later.
Clarify what you mean by multiverse, because there's different definitions of it, and I believe what you're talking about are these little pockets that are causally disconnected as opposed to say a parallel world or a bubble universe.
That's right. That's an excellent question. Extremely insightful. It's my wife asking the question. So you're right, and I was in fact vague about that just because this morning we were already talking about all those things, so I've said them already. But the word multiverse has different meanings in different contexts. What I mean when I was talking just now is what we call the cosmological multiverse, which is just a fancy way of saying that different regions of space could have very, very different physical properties. Like I said, either different cosmological parameters, like the density of energy, or different physics parameters, like the energy density of empty space, or even the number of dimensions of space. You could have a 6-dimensional region out there far away. There are other definitions of multiverse. The most popular other one is, of course, the many worlds of quantum mechanics. The idea from Hugh Everett that when you observe a quantum mechanical thing, like a spinning particle or a decaying nucleus, every predicted experimental outcome actually comes true, but in a separate universe. The wave function of the universe branches into many possibilities. We are not talking about that today. We're talking about the relatively prosaic and down-to-earth possibility that there are just different regions where things look different.
I forgot to remind you that when you ask a question, you should identify yourself. Thank you. Any other questions for Sean? Okay. Wait for the mic, too. Sorry. I'm so excited about this stuff. I'm forgetting.
It's very exciting.
Yeah,
Steve
it
Blau
is
from
exciting.
Physics Today. Did I hear Sean say that some of these other universes could affect ours? And if so, isn't that more or less classic testability?
Right. So there's two things here. That is a true statement, but not what I said. So the true statement is that there are certainly versions of multiverse theory where the existence of these other universes could literally be straightforwardly seen in evidence from our universe, such as the cosmic microwave background, or Alex Vlenkin has a new paper out saying that the existence of supermassive black holes could be correlated with the existence of a multiverse. The simple way this could happen for the microwave background is you imagine that two different bubbles of different kinds of space-time nucleate in the early universe and then expand toward each other. And our universe is one of these bubbles, and it literally bumped into another universe at early times. This could leave an imprint on the cosmic microwave background that is a falsifiable prediction. So that prediction has more or less been falsified. We have looked for those circles. We have not seen them. But of course, there's a parameter that varies. The likelihood of these bubbles colliding, is it 0.99 or is it 0.01? And you can't really say, well, it's a scientific theory if it's 0.99 and it's not a scientific theory if it's 0.01. It's just harder to know whether it's true or not if it's 0.01. But the point I was trying to make, which I didn't maybe say as explicitly as I could have, is the existence of these other universes, whether or not we can see them directly, affects how we think about the puzzles of our universe. So, for example, if there are no other regions where conditions are different, if there are no other regions where the value of the cosmological constant is different, for example, then our job as theoretical physicists trying to understand the cosmological constant is to come up with a formula that once and for all predicts the value of the cosmological constant. If there are different regions of space where the value of the cosmological constant is different, clearly it is a waste of time to look for such a formula, because there is no such thing as the once and for all value. The value of the cosmological constant changes from place to place. So the task that we have as physicists is a different one. Instead, we need to understand the distribution of different values and how they correlate with other observable features. So my claim is simply that even if you will never see the other parts of the universe where conditions are very different, whether or not they exist still affects how we do science in this universe.
Any other questions for Sean Carroll here in the room? Do we have any on the webcast?
Yes, we have one.
Okay, let's get the mic over there. Oh, you've got the mic, good, okay.
Okay. So the question is, and this is from Salvatore Nogui, some cosmologists, such as Lee Smolin, are defending we should give up the multiverse concept entirely, in essence because it became a lazy way to explain away the characteristics of our own universe as a random set of parameters. What do you think of that? And he is with the...
He's a freelancer from Brazil.
Yes.
Right. So I think that's not good advice. The point is basically, I mean, at the simplest level, the multiverse could be right. It could be true that there are other regions out there where physical conditions are very different. I think that if there is any principle that should guide our operation as scientists, is that we should not exclude a physically possible theory of the universe from consideration for purely philosophical reasons. The possibility that it's out there, if that affects how we do science here, is one we need to take seriously. That is not to say that there aren't lazy scientists who use this to explain this or that, but if there were lazy people who used a certain idea, we wouldn't have any ideas left that we were allowed to hold on to. So I think that we need to take it seriously, do the hard work, not either be too dismissive or too triumphalist. I don't think that the existence of a multiverse has already explained the value of the cosmological constant, for example. We need to take the problems of this scenario seriously without dismissing it out of hand.
Anything else? Okay, we're going to let you go, Sean.
All right.
Thank you
Thank
very
you very
much.
much.
A lot of thought-provoking things there. And if anybody needs to get in touch with Sean later, you can ask me. I can give you his contact info again. So now we'll take questions for Eric Craine and Evan Solomonides. Oh, you wanted to make an announcement? Sure.
If anybody is interested in learning more about the research that I did with Professor Yervant Terzian, the Cornell Media Office just posted a press release. The address is news.cornell.edu. Thank you.
Yeah, and I put that press release out via the AAS press service as well, so you should all have it. All right, questions for Eric Craine or Evan Solomonides from here in the room? I have one for you, Evan. You took as an assumption that we're average, and when you did that, you predicted that we really shouldn't start to wonder where everybody is for about 1,500 years. What happens when you start to vary your model and move us to one side or the other of average? I mean, how far away from average do we have to be before it could be millions of years before we hear? Or how far away from average do you have to move us before we really should have heard by now?
So actually, we assumed that we were in the median 95%. And so as long as we're in the median 95%, so not on the very first 2.5% of civilizations ever, and not in the last 2.5% to most recently arise, as long as we're not in the first or the last 2.5%, the 1,500 years is a fairly good estimate, but both of those, with us being exactly average to the 1,500 was a prediction, but we also analyzed if we were in the most recent 2.5%, and they were all fairly consistent results. It's at a far extreme, if our communication had just reached the nearest civilization and we were going to hear a response back if we were about to hear a response back that had reached them halfway between our first broadcast and now, if they had been reached and then immediately responded and we were about to get their response, then there could be as many as 78 million civilizations in the galaxy and we still wouldn't have heard a response.
Wow.
So there could be, the paper essentially just shows there could be life everywhere in the galaxy and we still wouldn't know. If we're waiting for a response, there could be anywhere up to 78 million and we still would not know.
Okay. Wait for the mic. Thanks.
This is Steve Blau again. I just want to know if this is sort of a reasonable, slightly different way about thinking of your result. So we've been broadcasting, I think you said, for, let's say, 80 years.
1936, Berlin Olympic Games, commentary.
Okay, so it's 40 years one way, 40 years the other.
Yes.
So I guess you're basically saying it's really unlikely that there's a civilization within 40 light years of us, I guess.
What we're saying, so our very upper limit on the number of civilizations that can reasonably be expected, broadcasting civilizations that can be expected, because we didn't look at where there could be primordial life. We looked at a broadcasting civilization. We said that if there was one within 40 years, then either they don't have the technology to answer us, in which case they're not really a fully sophisticated communicating civilization in the way that we were considering, or they don't want to respond and they don't want to be contacted, in which case, for SETI purposes, we don't care very much that they exist.
So if they don't like sports, we're not interested in them.
The very first broadcast, actually, Adolf Hitler, not a great way to start off.
Yeah. Right. Are there any questions from the webcast? Okay. Oh, you got one down here? Sorry.
Hi, Nola Red, freelance. So, Evan, how does this take into effect, like, when life evolved? I mean, if it got started earlier and if it got started later than it did around here, I mean, in terms of planets and evolving?
So it couldn't have started that much earlier because for life to arise, you do need a fairly high concentration compared to like the original galaxy. You do need a fairly high concentration of heavy elements. Like, life on Earth wouldn't be possible at all in any form without carbon, but sophisticated form we need iron, we need all the elements that exist in the human body. And so we were able to fairly confidently say that life, sophisticated life at least, wouldn't be able to exist that much before we were. But then a lot of what we showed was that because if one civilization arose in the Milky Way billions of years ago and sent out one powerful broadcast, we should have heard them. So part of what we showed is that life hasn't been around. There isn't that much of it, more than 78 million if they're all fairly young, but it also can't be that old. Because if it was very old, their communication should have been able to reach us.
Okay, sorry, did we do have some more on the web or not?
Yes.
Yep, okay, go ahead.
So the first question is from Salvador Nogui from Folha de Sao Paulo. It's for Evan. I was wondering, how would this apply to galaxy colonization instead of SETI? Would the Fermi Paradox be a paradox again if galaxy colonization is feasible?
If galaxy colonization is feasible, it essentially shows the same thing. They certainly couldn't colonize any faster than the speed of light, realistically, not anywhere near it. But as long as they aren't propagating their settlements faster than light speed, the exact same inequality and the exact same reasoning applies. Their fastest way to move forward in the galaxy would still be radio.
Okay.
And another question, this one's for Eric Craine. I'm from Anna Esvez from Sky and Telescope. Did his team take into consideration light from a city scattering in a direction away from the zenith?
Yeah, in the Lanai Index, you look really just at the satellite view directly down on the community. But in point of fact, because the satellite track precesses over communities, you can have images that have several different zenith angle views. And that's not incorporated into the Lanai Index, but it can become supplementary data for the community that you're interested in. And in fact, is some of the most important data that you can get. And when we talked about the follow-up measurements that we make, particularly the airborne measurements, we've developed what we call an airborne Gani Ometer, which is basically flying an airplane on a dome over a community and measuring the light from that community at a variety of different angles. And that's very important because what astronomers have been predominantly concerned about is light that's emitted just above the horizon and up to maybe about a zenith angle of 50 degrees. That's typically not measured, and in fact most communities are fairly unaware of its existence. We had an interesting example in Tucson, Arizona, very close to a number of major observatories, where one of the principal problems with lighting in that community is sports lighting. And what we discovered when we were doing aerial mapping of the region was that we could be in an airplane with the sports lighting between the airplane and the sporting field. We could be 5 miles away and 2 miles up, and the light was coming directly at the airplane. We were told by a number of people that was an impossibility because the specifications for the lighting were that it was extremely well shielded. The community had billed this lighting as dark sky friendly. It was anything but dark sky friendly. And because nobody was measuring it, they just didn't know. And so our argument is that things like the Lanai index and the follow-up measurements are extremely important because they are not modeling, they are actual quantitative measurements of what's really happening in the field.
Anything else? Any other questions from the room? Okay, back to Steve. Here comes the mic. We should just mic you up next time.
This is for Eric. So I think you described Lanai as an efficiency measurement, and maybe I missed it. But what's the numerator and the denominator in the efficiency?
Well, it's a little bit of a complicated formula, but basically what you're looking at is the radiance as a ratio to population, to numbers of housing units, and to area of the community. And there's a product of those ratios, and then it's normalized 0 to 100. There is a description of the formulation for this in the website that I indicated. So if you go to stemlab.org/LAN/OBS, there's a document there that describes in detail the structure of that formulation. And there are also graphics there that show those measurements in the field.
So if I'm a community planner or a mayor or something, and I look up my community on the index, and I'm not near an observatory, so there's nothing to compare to an observatory, it's just a number on the index. Is there a straightforward way to go from whatever I see for my community to an idea of whether it's good or bad, or I should improve, how I should improve, how I should strive to improve?
Yeah, a very good example of that is the work that we've been doing in Hawaii, where there was a specific community, Waikoloa Village, which has been very unusual in a good natural laboratory because it's almost exclusively illuminated by low pressure sodium, which was favored by the astronomical community. The lighting in Waikoloa Village was retrofit with filtered LED lighting to very great benefit for the astronomical community. The County of Hawaii Planning Commission and Department of Transportation is very interested in what's happening with other communities on the Big Island of Hawaii. And so they've been interested in a comparative ranking of those communities. And the percentile rankings of these Lanai indices provide that measure. And in fact, in the web reference that I just cited, you can find a copy of the posters that we did at the AAS meeting here, one of which describes that Waikoloa Village retrofit. And you can see in that how the community of Waikoloa has shifted with respect to other Hawaiian communities on the Big Island with respect to its zenith angle lighting index. And they were able to make a considerable improvement in the lighting of one community. They're now extending that to the others, but they're working through a priority list based on how good or how bad the lighting for a given community is.
Okay. Any other questions? Anything else online? All right, good. Well, thank you very much for your attention. Thank you for your presentations. And we look forward to seeing everybody tomorrow morning at 10:15. The press conference has something to do with gravitational waves and LIGO, and there seems to be a fair amount of interest in that. So I think we'll have an interesting morning. All right, thank you all very much. Signing off from San Diego.